7.5 Inverse circular functions. This is going to be the second to the last section in chapter 7. There are only, well, actually there's 7 total sections, but we're going to skip the 7th one. That one goes over like 1 or 2 problems, and they're not really that important. So 7.5, 7.6 are the last 2 sections in chapter 7 that we're going to be going over. 7.5 and 7.6 kind of go hand in hand. 7.5 is in preparation for 7.6. So for 7.6, we're solving trigonometric equations. And a lot of the times that requires us being able to calculate inverse trigonometric function values with a calculator offhand right away. So we need a section on the inverse circular functions to get a better understanding of how they work, because in the context of an equation, it gets a lot more complicated than just plugging into a calculator and taking an inverse sine, inverse cosine, inverse tangent. So there's a lot more at play here that we need to understand. So we have an entire section over them that we're going to try to understand to the best of our ability. So we'll start off with the simple, or as simple as I can make it, a simple review of inverse functions. And we start off with all these basic terms that we've seen in Algebra 1 and then in Algebra 2 later on. So we'll start off with the most basic term that we've seen in Algebra 1, which is called a relation. So it starts off with a relation. So the word relation, and we use a symbol r to denote that, and it's a relation on the Cartesian coordinate plane, and that distinction is there because relations are way more abstract than just things that we've seen in Algebra 1, Algebra 2. Algebra continues on past high school into college, into postgraduate studies, postdoc studies, and it's still a very vibrant area of mathematics. So there's all these different algebraic spaces, geometrical spaces, topological spaces for which we have relations and functions and things like that. And it gets kind of out there. So I have to make the distinction on this elementary idea that we call the Cartesian coordinate plane. We'll define a relation that way. And it's going to be a little bit doable, hopefully. But yeah, we have to make the distinction. So we're only talking about things like this on a two-dimensional coordinate grid. X and Y are rectangular coordinates, which are real numbers. So a relation, we'll just think of it as a set of ordered pairs, which that is not the rigorous definition of a relation in mathematics, but it's going to work for our intents and purposes. So it's an ordered pair, or it's a set of ordered pairs, sorry. It's a bunch of ordered pairs, things that look like this, x comma y. You have an x coordinate and a y coordinate. The first number x is what we call the x coordinate. And that's just a number, a real number. The second number, y, called the y-coordinate. And that's just another number. And they're ordered, so that way x is first, y is second. Okay, so for a relation, we call the set of all possible x-coordinates that appear in the relation R the domain of that relation. So domains are not just for functions, they're specifically for relations first. We can use a symbol, d, to denote the domain. Sometimes we get more specific, let's say like this, d with the r in subscript. That's if I have multiple relations and you want to say, well, this is the domain for this relation, dr. Equivalently, the set of all y-coordinates, we call that the range of the relation r. So we can also write it r with an r in subscript, where the r in subscript is the relation name r. So domain and range. So the idea is that what we have graphed are two relations. They're both relations. They look different, and we categorize them by the way that they look. In this case, we call this one a discrete relation. This one here we call a continuous relation. And it's not so much that the relation is discrete or is continuous, it's the sets, the domain and the range that make up the relation, which are discrete or continuous. And you can have a combination of the two as well. It can get kind of weird. But for these two things, these are both relations because they're literally just sets of ordered pairs. These are discrete points, whereas these are connected points. If you remember in geometry, a line is thought of as just an infinitely connected set of points on a continuum, basically. So they're both sets of ordered pairs. And we can go into the details of finding the domain and the range for each of those, but we're going to skip that because that's beneath us. We're in a pre-calculus class. We've seen that tons and tons of times. So we'll continue on. So a relation in the Cartesian coordinate plane, we want to make a distinction. There's a special type of relation that we study in algebra. These are functional relationships. And the way that mathematicians understand functions is they first think of them as relations. So they have to go through all this work to study relations at a very rigorous level, and that's how they're able to achieve a definition for a function. So a function is a type of relation, and in this point, or in this particular class, there's a certain way that we can get this done. We'll choose an intuitive route. There's many ways you can define a function. There's a very rigorous and precise way to do it, but we're not going to do it that way. We'll just go with what's intuitive in the situation that we're working with on a coordinate grid. And we talk in terms of a vertical line test. So we'll go ahead and say a relation either passes or fails that vertical line test. We'll define what it means to fail the vertical line test. So a relation R fails the vertical line test, which we normally abbreviate it, if I wanted to be lazy, VLT for short. So I write VLT, it stands for vertical line test. So a relation on the coordinate plane fails the vertical line test if there's a vertical line that we can draw that contains more than one point on the relation R. So what we've seen in Algebra 1 or in Algebra 2 classroom, if I can draw a vertical line and that vertical line intersects R more than once, it fails the vertical line test. And we check to see whether or not it passes the vertical line test to see if it's a function. So it fails vertical line test if there's a vertical line that crosses more than once. Otherwise, we say it passes the vertical line test. Now, a relation that passes the vertical line test is known as a function. That's how we'll define a function in this course. So a function is a relation that passes the vertical line test. And what we can do, we can check really quickly to see which of these pass and fail. So if you look at the one on the left, that one passes because there's not a single vertical line that I can draw that'll cross this thing more than once. So there are a total of, I think, 5 different lines I can draw, and for each of those lines, you'll have a maximum of 1 intersection point. So this passes the vertical line test because there is no line that I can draw that passes more than once. So it passes the vertical line test. Now if you look at the second one, this one obviously fails the vertical line test. And you can check quickly, there's a line that I can draw where the intersection points are more than 1. So this one has, I found a place where there's 4 intersection points. This one fails. This one passes. And what about this one? If you wanted to get really technical and you want to be kind of like a troll, you can say this one fails. And what do I mean by that? You can draw a vertical line this way over here, and you can say, well, the arrow, that's not an arrow, that's part of the actual relation. In that case, you can find a place where there's 3 intersection points. But a lot of the times, if you draw an arrow like that, what that arrow really means is that it continues going in that direction, in that pattern. Right, so if you were to just think of that as a directional arrow, then no, this one passes the vertical line test. If it continues in the pattern that we assume it's going to continue in, then this is going to pass. And the ones that pass are functions. The ones that fail are not functions. They're just simply relations that are not functional. So the ones that pass are functional relations. The ones that fail are not functions. They're just relations. So then we keep on going. So the idea then, in Algebra 2, they introduced the idea of a functional inverse. The reason being, it's because we think of equations in Algebra 2 at a very, very rigorous level compared to maybe Algebra 1. Algebra 1 is very basic, but in Algebra 2 you could think of equations in terms of functions. You have functions set equal to each other, or maybe functions equal to a number, and you can solve an equation by taking a functional inverse of that equation. So we study in Algebra 2 the idea of a functional inverse, and the way that we can establish that here in this course is we'll start with a relation again, not a function just yet. So we'll start again with a relation. So a relation, if you want to put this in more mathematical symbols or something that's a bit more mathematically based, you take a relation R, and that's the name, and then we construct what it is using this mathematical thing. We call this set builder notation. So that's kind of a fancy thing we might have seen in Algebra 2, set builder notation. And mathematicians use set builder notation to communicate to other mathematicians, this is what this set looks like. This is how you build that set or construct the set. So what it's basically saying is R is the name of the thing that we're trying to build, and it's a set. Set meaning we have these two curly brackets. We start a list that way, and it's a set on the left of this vertical bar. It's nothing but a bunch of these things. Two number pairs, ordered pairs, x comma y. The stuff to the right, all this stuff out here of that vertical bar, those are conditions that that thing to the left, x comma y, satisfies. So we take ordered pairs, x comma y, such that the first condition, x is a part of a domain, D. Y is part of a range, R. So they're just real numbers. So both x and y are real numbers, and we're going to go ahead and think of all the x numbers as part of a domain and all the y numbers as the range of a relation. So that's all that's saying. So R is going to be just a bunch of x comma y's. So that's the case. We continue going. Let me go ahead and write in black. We're going to call it the inversion. So I'll make a distinction between two different things. The inversion of a relation, and then later on the inverse of a function, right? Because not all relations are functions, but you can invert all relations though, in a certain sense. All right, so we're going to take an inversion to be a geometrical thing, a geometrical transformation. So the inversion of the relation R, we're going to denote it by R with an inverse symbol, R to the -1 power. That's not a reciprocal power thing. That's just to denote a relational inversion. So then we take the relational inversion to be the exact same thing as R, except we swap x and y. We switch the roles of x and y. So what we're doing is we're reversing the order. So ordered pairs, x is first, y is second. If we reverse the order, we introduce what's called an inversion. So we're just flipping x's and y's. So what we're going to try doing is with this particular graph that I have here to the bottom, we're going to try to graph its inversion based off of the graph that's given here. So I'm going to take this one in black, and I'm going to call that one R. And what I'm going to do is I'm going to list all of the ordered pairs, or some of the ordered pairs, that are on there. So R contains, so it's not going to be equal to this, but I'm going to be making some notes here. So I'm going to list some of the points in there. That's not going to be all of the points, but only the ones that we can obviously see here. Let's say if I circle that one to the left, that's the ordered pair -5, comma, -2. And it really doesn't have -5, -2 in there. This one doesn't actually live inside R because it's an open circle. But I'm just keeping track of it because I want to know what to graph here. On the inverse, if that was a point on the relation R, then we invert it. That's -2, -5, and that's the one that's going to be corresponding to -5, -2 in R, for R inverse. So I'm going to keep on going. The next point I can kind of see as a reference, so I'm really just tracking reference points. -3, 2. What you do is you reverse x and y, so 2, -3. So reverse the order, and that's going to be a point I'm going to plot also. Next one that I see, 0, 2. These are just points that I'm picking out that are easy to see. 2, 0 would be its inversion. Next one, 2, -2. And its inversion would be -2, 2. I see this other point here at 3, -2. Its inversion, -2, 3. This point, 4, 0. 0, 4 would be on the inversion. This last point here, not there, at 5, -2, should correspond to a point -2, 5 on the inversion R. The truth is R inverse contains many, many more points other than that. All the points in between where those lines are at, actually it also doesn't contain that point because this one's an open circle. Open circles are not contained inside. So put a bunch of dots here because there's more points than just those. All I'm doing is I'm drawing the corners basically, or keeping track of the corners. So what I'm going to do is maybe in red, draw the inversion. And the first point, which I have crossed out, -2, -5, is an open circle. It's crossed out because it's an open circle. And then if I keep on going, the next one I see is 2, -3. So 2, -3 is over here. I need to draw a straight line through both of those. to the best of my ability. Yeah, that's fine. 2, 0 is this one. Straight line through those. Negative 2, 2. So negative 2, 2 is here. Straight line through those. The next point after negative 2, 2, I see negative 2, 3, which is up here. Straight line through those. Then 0, 4. And then 5, negative 2. Oh, sorry, negative 2, 5. Okay, so here what we've done is we've drawn the inversion of a relation that was already given in black, and the inversion is drawn in red. So take a good look at those two, compare the two. This is what it looks like to take a relation and invert it. So what we're doing is we're swapping the x and the y coordinates. So whatever the x coordinate was, it's now the new y coordinate. Whatever the y coordinate was, it's now the new x coordinate. And you plot all those points. So one thing that you might remember from Algebra 2, or maybe from the beginning of this course, at the beginning of the year for this particular course, the inversion and the original are symmetric with respect to, so they're reflections of each other about y equals to x. And that's how you can cover, or that's how you can create or construct the inversion of a relation or a function. Same thing with functions too. So that's the first major thing that we need to be aware of and understand very, very well if we're going to be understanding what the inverse of sine, cosine, and tangent look like. So we're going to be taking a piece of the graph of sine, cosine, and tangent, and then finding its inversion as a geometrical entity, and then seeing if we can come up with a restriction that will allow us to come up with a way to invert expressions containing sine, cosine, and tangent. So more details on that in a little bit. So we'll keep on going. So a couple of things before we do that for sine though. A function is said to be, we're going to call it 1-to-1, because we can invert any relation, right? So I could take a relation and find its inverse, as shown here. So any relation we want, we could just take its inverse or invert it geometrically that way. But the ones that we consider important, that are useful in algebra, are those that are what we call 1-to-1. So if we have an x coordinate that maps onto a y coordinate, it better map onto a unique y coordinate, and vice versa. Every y coordinate in the relation needs to be mapped back to a unique x coordinate. So that way we can solve one given the other in either direction. So functions for which that's actually possible are called 1-to-1. Now, the way that we define 1-to-1 here may not be the way that you would see it in another maybe higher level algebra textbook, but in this course, this is good enough. So we say that a function is 1-to-1 if the inversion of the function f is also a function. So if the inversion of a function happens to be a function as well, then we call that function 1-to-1. So we can check to see if the one that we just drew was coming from a 1-to-1 function. Is the relation in black 1-to-1? My answer will be no. And what we do is we check the one in red. Is the one in red a function? No, it's not. And because the one in red is not a function, the original function is not 1-to-1. So a function is 1-to-1 if its inversion passes the vertical line test. Now, if you remember from the beginning of the course or from Algebra 2, a function is also 1-to-1 if it passes the horizontal line test. Horizontal line and vertical line are inversions of each other, though. So if you take a horizontal line and invert it, you get a vertical line. If you take a vertical line and you invert it, you get a horizontal line. So there's the distinction between them. That's how they're related. Okay, as a real quick corollary, corollary just means that that's something that directly follows from the previous line. So as a corollary, the inversion of a 1-to-1 function is also 1-to-1. And that's quick to check. So if a function is 1-to-1, it passes both the vertical and the horizontal line test. So then its inversion should also do the same, pass both the vertical and horizontal line test. That's easy to check. So we'll talk about the inverse sine function. So if you remember sine on a unit circle, which that's why I have a unit circle to the left, sine on a unit circle is the y coordinate. Let me zoom in on this. The x-coordinate is cosine. The y-coordinate is sine. So we take whatever angle. Let's say this is the angle theta. We start on the positive x-axis, and we measure counterclockwise from the positive x-axis for angles, and that's what we call standard position. So sine, we started off with y, or not y, theta equals to 0, that's here, and then we track the y-coordinate as we go this way. And we've already seen how to graph those. Those are pretty simple. So what I'm going to do is I'm going to use this as a coordinate plane here, and we're going to graph a piece of the y is equal to sine theta. So we're going to call this theta on the horizontal axis, and this one y. We'll keep that one as the y, since y is the sine, or sine is the y. Okay, so we can start this at 0 radians, end this at 2 pi radians. Cut this in half, we get pi radians. Cut this in half again, we get pi over 2. Cut this in half, we get 3 pi over 2. And that's here. 0 radians, pi over 2. Pi is the half circle. 3 pi over 2 is the y-axis pointing down. And then over here is 2 pi where 0 is at. So 0 and 2 pi are essentially the same place, the same location. Different angle to get there though. But in either case, so what I'm going to do is I'm going to draw a vertical line or a horizontal line this way so I can track the y-coordinate and line them up. And then we'll draw a sine curve. Sine curves you should be very familiar with. We know it starts at 0. When it's 0, pi over 2 is 1. At pi it's 0. 3 pi over 2 is -1. 2 pi it's 0 again. And we have this curve, which I'm going to draw in 4 pieces, because I'm going to eventually erase some of these pieces. And there's our sine curve for 0 to 2 pi. Now we can also track this going backwards this way. And if I track this going backwards this way, a full circle, what that is on the graph is a mirror image of what's on the right side, kind of, somewhat of a mirror image. So let's say this is -2 pi. It's just a repetition of the information that's on the right. So -pi, -pi over 2, -3 pi over 2, and so on. So if I wanted to draw this over 2 periods, we totally could. It's the same pattern. This one's at 0, this one's 0, this one up here is 1, this one down here is -1. And it's just a continuation to the left. And again, I'm drawing it in 4 pieces because I'm going to erase a lot of these pieces, keep some pieces. So to the best of my ability, there's 2 periods for sine. From -2 pi to +2 pi fits 2 periods. So that's the graph for sine. We're very familiar with the graph of sine. So what I'd like to do is generate the graph for inverse sine. So inverse sine, hopefully as a function, if it's a function, what we do is we invert the graph. So inversion done this way. So inversion like we did in this problem. So I'm going to take the graph we just drew for sine and we're going to invert it, or find the inversion of it. And to do that, you swap the horizontal and vertical components. This is no longer theta, now this is y, and this is theta. Theta is going to equal to the inverse sine of y, if it exists as a function. So we'll draw it as an inversion of a relation, and see if we can try to understand it as an inverse of a function. Now before I do that, I might want to label my axes. So y goes from -1 to 1, and it's going to range this way instead. That's my domain now, no longer my range. So we're thinking vertically now. It's going to be a vertical wave instead of a horizontal wave. Now if theta is the vertical axis, this is 0 down the middle. It's going to end up here at 2 pi. If I cut this in half, this is pi. Cut this in half, this is 3 pi over 2. If I cut this interval in half, that's pi over 2. And then I want to go backwards. -2 pi, -pi, -pi over 2, -3 pi over 2. And then we try to draw the sine curve. So this might look a little weird at first, or a little strange at first, but we try to remember what those points are. 0, 0. All right, so I'm looking at the one to the left to help me cheat a little bit. So at pi over 2, y was 1. So when theta is pi over 2, y is 1. So that goes there. When theta was pi, the y coordinate was 0. When theta is 3 pi over 2, the y coordinate's negative 1. And then at 2 pi, y is 0 again. So if I try to draw this, it's going to look something like this. It might come out a little ugly, but all my graphs kind of come out a little ugly. So something like this. And if I continue it backwards, I'm basically just copying what I have up there at 2 pi backwards. So this way. This one hits at 0. I could have done a better job on that one. At 3 pi, it hits 1. And then at 2 pi, back down to 0. So something like this. So there's the inversion of sine theta. So when we take an inversion, you're just swapping the x and the y coordinates, or in this case, it's the theta and the y coordinates, because the x coordinate, we're not using x coordinates for cosine, and cosine will be another problem. But that's what the inversion looks like. So there's a bit of a problem here. Sine is not 1 to 1. You can obviously tell it's not 1 to 1. So you can check on the one on the left, the one in the middle, that is. Sine's not 1 to 1 because if you drew a horizontal line somewhere, you can find a horizontal line that crosses more than once. If you look at the one on the right, you think of a vertical line then. Horizontal line on the left is a vertical line on the right. So you draw a vertical line, and this thing will fail the vertical line test if you draw a line between negative 1 and 1. Right, so sine is not a 1 to 1 function. Therefore, the inversion of sine is not a function. But what we do then, we'd like to still think of the inverse sine as a function that we can define for calculator purposes and solving equations and things like that. So the way that we get this done is that we cut off a bunch of pieces from the sine curve to see if I can make the inversion a 1 to 1 function. So there's several ways we can attack this, but I'll just cut straight to the chase. The pieces that we cut off are everything that is not inside negative pi over 2 to pi over 2. So we only leave this piece here, from negative pi over 2 to pi over 2. So negative pi over 2, here's the left boundary, and here's the right boundary. And here, what that refers to would be everything to the right of the y-axis, all of this stuff. So we're going to define inverse sine for angles on the right half only. So inverse sine is on the right half. Now let's see what that looks like on the inversion graph. So on the inversion graph, that's vertically from negative pi over 2 to pi over 2. So we're cutting out all of this junk. And we're only seeing the stuff from negative pi over 2 vertically. So from down here, all the way up to up here. So pi over 2. So that's what those look like inverted. So now sine is 1 to 1. Inverse sine is also 1 to 1. But we have to be careful what the domain and the range are. So we're restricting the domain for sine. So that way theta is between negative pi over 2 to pi over 2. That's the important piece. That's the domain that we cover this for. And if that's the case, the range for sine is still going to be restricted from negative 1 to 1. Also very, very important. So the y-coordinate, of course, has to go from negative 1 to 1. The theta value is restricted from negative pi over 2 to pi over 2. So what is this? What's the importance of this? This is how we define it mathematically all across the board pretty much. This is how calculators are programmed to work with inverse sine. Inverse sine on a calculator or on other computer calculators and stuff like that. They define inverse sine for angle values only between negative pi over 2 to pi over 2. So if you use inverse sine in a calculator on a computer program, it's only going to spit out a number between negative pi over 2 to pi over 2. So that's the major thing that we're trying to learn in this particular section. What the ranges are for inverse sine, inverse cosine, and inverse tangent. And once we learn what those are, it gets a little easier for us to solve more complicated equations. Okay, so we'll continue on. So that definition there is basically just driving home what we have up here visually. So we're going to define then theta to equal to the inverse sine of some number y to be the angle that's between negative pi over 2 to pi over 2 only that makes sine of the angle theta equal to y. So these are the two most important formulas. So y equals sine theta is the same thing as theta equals inverse sine of y. And that's if and only if theta is between negative pi over 2 to pi over 2. Very, very important. So that's how we're going to transform backwards and forwards between y and theta. So we're going to practice that a little bit with example number 1. So in example number 1 here, I have a unit circle there to practice with. So visually again, we're only going to be allowed numbers on the y-axis between negative pi over 2 and pi over 2. So I'll draw the right half. So we're only allowed these numbers on the right half for sine and sine inverse. So that's the first thing that we need to remember when we're simplifying expressions of this type. First major thing. So we'll start with letter A. Now letter A, it says y is equal to arcsine, and that's a typo, and I thought I fixed it, but I didn't fix it. Those should be thetas. So theta is equal to arcsine of square root of 3 over 2. Arcsine is another way of thinking of an inverse sine quantity. They're not exactly the same thing, arcsine and inverse sine. So I think arcsine predates inverse sine. The usage of the term arcsine is actually the original usage of it. And it's the same way that sine, cosine, tangent, those functions were first introduced. They were first introduced in the context of geometry. So in geometry, we use arcsine if you're studying geometry. In this case, we're not studying a strictly geometrical concept. This is a combination of geometry and algebra. But arcsine refers to angles on a right triangle, and then the extensions of angles on a right triangle in a geometrical situation. So arcsine was the original way that those were denoted. Algebra came along, studied functions and inverses of functions, and inverse sine for a restricted domain is actually the same thing as an arcsine. So in this course in precalculus, we're just going to consider them to be the same thing, arcsine and sine inverse. So you might see arc cosine or arc tangent and stuff like that, but they just refer to the inverses. So it's just a fancy way of saying inverse sine. So they mean the same thing in this class. So in this class, we consider them the same thing. That would be a lie rigorously, but not in this class. They're functionally the same thing. So whenever they ask for theta equals to arcsine of square root of 3 over 2, we're really looking for the y-coordinate equal to square root of 3 over 2. And we're looking for the angle theta that makes the y-coordinate equal to square root of 3 over 2. So where did I get that from? I'm using this right here. The very first line. If y is equal to sine theta, then theta is equal to sine inverse of y. So we started here. Theta is equal to sine inverse of some y quantity, then sine of the theta is equal to the y quantity. So sine of theta is equal to this quantity, square root of 3 over 2. So we're looking for a y-coordinate equal to square root of 3 over 2. That would be up here. If you remember your unit circle, this point at theta is equal to pi over 3, which is the same thing as 60 degrees. So the same thing as a 60-degree angle. The x-coordinate's 1/2, the y-coordinate square root of 3 over 2 at 60 degrees or pi over 3 radians. So we're looking for that angle, and it's this angle, square root of 3 over, or pi over 3, sorry. So theta is equal to pi over 3 radians. And that's it. So we're literally just looking for the angle that makes the y-coordinate equal to what they gave inside. So the y-coordinate was square root of 3 over 2, that's y. What's the theta value on the right circle, the right half of the circle? That makes sine that y-coordinate value. So if we try this for letter B, theta is equal to the inverse sine of negative 1/2. What we do is we plot negative 1/2, and I believe that's this angle right here. Y coordinate is negative 1/2. We want the angle theta. That makes that the case. So the angle theta, that would be what? Negative pi over 6 is what it's going to spit out. So this is where the x coordinate is square root of 3 over 2. The y coordinate is negative 1/2. So it's at negative pi over 6. So theta is equal to negative pi over 6. And why am I writing it as negative pi over 6? You might remember when we did unit circle a long time ago, so back at the beginning of chapter 6, we used to report this angle from here to here, which that is 11 pi over 6. Why am I writing it as negative pi over 6 when back then I would have said that's the wrong way to do it? You want to write it as a positive number between 0 and 360. So the reason why we're doing it this way at negative pi over 6 is because it follows this rule. The angles are supposed to be written so that way they're between negative pi over 2 to pi over 2, negative 90 degrees to positive 90 degrees. They have to be written that way, and that's the way the calculator is going to give it to you. If we're just trying to understand these functions the way they are and the way that they're defined. So we'll look at letter C. Theta is equal to sine inverse of square root of 2. So if I rewrite that, square root of 2 is equal to sine theta. So is there a theta that makes sine square root of 2? So if you have a little bit of number sense, square root of 2 is a number that's bigger than 1. 1.4142 something something is what square root of 2 is approximately equal to. Keeps on going, and it's a random pattern. So the problem with this is, does sine ever correspond to a y coordinate? Remember, this is a y coordinate that's equal to 1.41-ish. And the answer is going to be no, because if I try to plot a point on the unit circle with a y coordinate of 1.414 ... it's going to be up here somewhere. But there's no point on the unit circle that has that y coordinate. It's too far out. Y coordinates are restricted between negative 1 and positive 1. So if I get a number that's outside of that range from negative 1 to positive 1, this cannot happen. So sine does not exist, or is undefined at that point. Just a quick example, example 1. So practicing the definition of, or applying the definition of sine inverse. So what we're going to try doing now is coming up with those definitions for cosine and tangent as well.